the input CTs are 2000 amperes by 400 milliamps, and the output CTs are 1000 amperes by 200 milliamps, and the PT is present are 4000 volts by 50 milliamps. The pre-charging contactor rating would be 1800 volts to 50 amperes, and the main contactor rating is 2000 volts, 1500 amperes, and the resistors, the bleeder resistors that are used to discharge the DC link, so are of 6 into, so 6 number of resistors will be there, then each one of 1.8 kilo ohms, and the power wattage is 500 watts, and the CT is of 1000 amperes by 1 amp, the pre-charging resistors, so 4 number of pre-charging resistors will be there, so that of 4 into 6.25 ohms and 800 watts, and the IGBT ratings present in the line converter modules are 4.5 kilovolts, 1.2 kiloamperes. So next, the ELD resistors, that of 3 into 22 kilo ohms and 3 into 6.8. So as we have seen the earth leakage detection circuit resistors, and the filter capacitor is of 4.25 millifarads, and the DC link capacitors, 8 number of capacitors, each of rating 1500 microfarads, and a total of 12 millifarads. And the coolant pump. The coolant pump is of 3-phase, 415 volts, 2.2 kilowatts, and 2900 RPM. And the turning fans present in the control unit are 48 volts DC. And the coolant used for cooling the IGBT modules are ethylene glycol plus water mixture, that is of 30% of ethylene glycol and 70% of water. And the make is Clariant anti-frozen type, and the ESW earth switch, that is of 3 kV DC, 400 amperes, and 2 volt. And input voltage range is of 863 volts to 1523 volts, that is single phase. And ADU, the analog distribution unit, the input is 110 volts DC, and the output is plus or minus 15 to 24 volts DC. So these are the ratings of the capacitor. So next, we will be discussing about the analog distribution unit that is present in the line and traction converter unit. So the type of this analog distribution unit is M628 ADU. So this is the analog distribution unit. Here you can see the analog distribution unit here. So this is present on the top of the line and traction converter unit. So M628 ADU is an analog distribution unit located in the LTC. So it serves the purpose of supplying regulated DC power supplies to the various sensors present in the locomotive, such as current, pressure, temperature, and speed sensors. And it also does the collecting and transmitting the data or the output signals to the line and traction control unit. So the unit consists of 3 plug-in type bayonet connectors and 18 D-sub connectors. So here you can see the 18 D-sub connectors. These are the D-sub connectors, and these 3 are the bayonet connectors. So one number of bayonet connector is used for 110 volts DC power supply source, and the rest 2 are for the signal. So from one connector, so from this connector, we will be getting the 110 volts DC supply to the ADU here, and the rest 2 connectors are for collecting and transferring the signals. And these sub connectors are connected to the various sensors. So these are all the D sub connectors. So these are connected to various sensors in the locomotive. So here you can see the clear picture of the ADU here. So these are the 3 bayonet connectors, and these are the D sub connectors. So these will be connected for various sensors, and from here we are getting the 110 volts DC supply from the locomotive battery, and from these 2 bayonet connectors we are getting the signal. The unit consists of the regulated power supplies required for the sensors. So these regulated power supplies are operated on the 110 volts DC input power supply, as we discussed from the locomotive battery. And the 110 volts DC input is fed to the MLF, that is the MEDHA line filter, to remove the unwanted signals. And the filter output of the MLF is fed to the ADB-PS, so analog distribution box power supply, to convert the 110 volts into the required DC voltage level for the operation of various sensors. So for operation of various sensors, the 110 volts is divided into regulated outputs. And all the sensor outputs are connected as inputs to the respective analog input card. As we have seen, the analog inputs coming to the analog input cards. So from the sensor, it is coming to the analog input card into the control unit through the ADU, analog distribution unit, for proper routing. So the D type of subconnectors. So these are the connectors here, sensor connector details. So there the nameplate will be like AA, that is the primary current sensor, and AC, auxiliary current, auxiliary circuit current sensor, and for AE, the harmonic filter current sensor, and AI, transformer oil pressure sensor, and AG, total load current sensor, and DA for TM1 temperature sensor, and DC for TM2 temperature sensor, and DE for TM3 temperature sensor. In the same way, DI, transformer oil temperature sensor, and HA is a TM1 speed sensor, HC is the TM2 speed sensor, and HE is the TM3 speed sensor. So these are the DC connectors used. So for safety purpose, in the line and traction converter, so we are given earth switch, reader resistors, and the LED indication of the DC link. So by earth switch, by operating the earth switch, the one maintenance person can approve that it is safe. And for discharging the DC link, so these breeder resistors are used. So during the off condition, the DC link discharged by the breeder resistors here. And for instant discharge of the DC link, so earth switch is also operated here. So in order to see the voltage in the DC link, so in order to check the voltage in the DC link, so once the maintenance person can see this indicating uh, LED here. So if the LED is blinking, the frequency of the LED is very high, blinking frequency. So one could understand that the DC is not discharged here. So once the LED is stopped blinking, so the person can proceed for the maintenance. So these are the safety measures and protection equipment given in the line and traction converter unit. So next, protections. So here we are having the DC link protection. So the DC link protections are like DC link over voltages, DC link short circuit protections, earth leakage protection, and in the same way, traction inverter side protection. So in the traction inverter side protections, we are having the output overcurrent protection, output short circuit protection, IGBT heatsink over temperature protection, and traction motor over temperature, and traction motor over speed, and phase imbalance protection. So these are the protections of traction inverter side protection, and these are the DC link protections. So next, coming to the topic of redundancy. So here we can see the type of failure and the effect on the locomotive. So this redundancy in line converter computer. So this is the line converter computer redundancy. So in the line converter computer, so if the type of fault is communication fault, so there will be no reduction in the locomotive power. So because we are having the communication of main and redundant channel are also available here. So if any damage in the main communication channel, so we are having the redundant channel for the communication purpose. In the same way as we have seen in the line converter computer, we are having control cards, analog cards, and DIO cards. So in that, if you are having any failure in the control card, the reduction of the 1 by 4th of the locomotive power will be reduced. So that means one line converter will be isolated there. So total including the line converter, so LTC1 and LTC2, that is SR1 and SR2. So including both, we are having four number of line converters. So if one converter is failed, so the other three will be in operation there. So that the reduction of 1 by 4th of the locomotive power is given. So in the same way, analog cuts. So if analog cut is failure, in the same way reduction of 1 by 4th of the locomotive power will be done. And the power supply card, so reduction of 1 by 4th locomotive power. And in the same way DIO card. So if the DIO card is failed, so no reduction in the locomotive power. Same DIO channels are allocated from both LICs. So if one DIO is failed, is detected by the LIC, then the other DIO will be taking charge. So up to now we have seen the redundancy in the line converter computer. So next we are going to see the redundancy in the traction motor computer. So this is the line converter computer and this is the traction motor computer. So in traction motor computer we are having a power supply card, control card and an analog card. So if any failure in that card, so what is the reduction we are going to see? Then what is the effect in the locomotive? So if there is any failure in the communication, so in the same way effect on the locomotive will be no reduction in the locomotive power because as we know the main and redundant channels are available here. And when a control card is failed, so when a control card is failed, reduction of 1 by 6 of the locomotive power is done. So 1 by 6 because so including the SR1 and SR2 we are having 6 traction motor computers here. So we are having in SR1 three traction motor computers for operating the three motors, and in also in SR2 for operating three motors, we are having three traction motor computers. So totally we are having six traction motor computers. So if one control card in one traction motor computer is failed, so that will be isolated. So that reduction of 1 by 6 of the locomotive power is done here. So in the same way, analog cards, same reduction of 1 by 6 of the locomotive power is done, and power supply card, so reduction of 1 by 6 of the locomotive power is done here. So this is the redundancy about the line converter computers and traction motor computers. And we are having some more redundancy. So that is the IGBT open circuit failure. So if any in any module, if an IGBT open circuit failure is occurred, so there will be a reduction of 1 by 6 of the locomotive power. And in the same way, gate drive card, so reduction of 1 by 6 of the locomotive power is done. And gate drive power supply card, same 1 by 6 of the locomotive power. And if there is any short circuit issue on the IGBT, so totally half of the locomotive power will be reduced there. And speed sensor, no reduction in the locomotive power. So if at least one quadrature signal is available in there, so we are having if we are having at least one quadrature signal is available, so there will be no reduction in the locomotive power. And temperature sensor, so no reduction in the locomotive power because two temperature sensors are available in one traction motor. So if one is failed, the other one will be the redundant for that. And OVL IGBT, over voltage protection IGBT module. So no reduction in the locomotive power. So if IGBT fails in the open condition. So these are some of the redundancies. So next coming to the maintenance. So periodical maintenance of LTC unit includes the following procedures. So these are the periodic maintenance procedures here. So the first one is the visual inspection of liquid connection. and coolant refilling, and spill-proof connector maintenance, and visual inspection of transformer link and motor cable connection. So here we can see the connections here. So these connections should be checked there. The output for the input for the motors are given from this. So these connections, tightness of the cables. So here you can. So next, this is the coolant section. Here we can see the coolant pump. So this is going to the radiator here. So here we should check this tightness or leakages of the coolant. So here we can see the system should be thoroughly checked for corrosion, scale, and sedimentation, and color and pH of the coolant to be monitored quarterly, and coolant normally to be changed after every 3 years. So accepted pH range of coolant is 7.7 to 8.3 during filling condition, and 7.1 to 8.9 while in service. So next we will be discussing the auxiliary converter here. So this is the auxiliary converter, and this auxiliary converter is used for supplying the auxiliary load as we have now. So here is the block diagram for the auxiliary converter. So actually we have two number of auxiliary cubicles as we have discussed in the first session. So this is the auxiliary cubicle 1. Here we can see the auxiliary cubicle 1, and this is the auxiliary cubicle 2 here. And auxiliary cubicle 1 will be having auxiliary converter 1. So that we call it as AC1 here. And in auxiliary cubicle 2, we are having two converters, that is AC2 and AC3. And including the in the auxiliary converter cubicle 2, we are also having the battery charger unit. So that we'll be discussing in the next slide. So coming to the block diagram here. So first, the in the same way the OHC 25 kV, 25 kV 50 hertz nominal voltage. So through the pantograph, so it is coming to the vacuum circuit breaker or TJ. So through that, so it is coming to the transformer, locomotive transformer primary winding. So here we can see the primary winding. After that, there will be a filter winding there. So after that, in the secondary, we are having the auxiliary winding. So this is the auxiliary winding here. So the auxiliary winding is supplying for the auxiliary converter. So the rating of the auxiliary winding, as we have seen, the voltage is 100,000 volts and the power rating is 334 kVA. So the 1000 volts input is given to the auxiliary converters, both auxiliary converter 1, 2 and 3 parallelly. Here we can see the supply is parallelly given to the every converter here. So after the supply is given in the input section, we have some protections there. So we have the fuses connected for the overcurrent protection, and MOVs for input surges protection. So the MOVs are metal oxide variative. So after that, we are giving to the semi converters here. So semi control converters. So in this semi control converters, uh, so so before giving to the semi control converters, we are also having the earth leakage detection circuits here. So ELDs, we have called as ELDs. Both in input and output side, we are having the. So here we are having the semi-control rectifiers here. The function of semi-control rectifiers is, so in this semi-control rectifier, we are having uh, thyristors in one leg and diodes in one leg. So the purpose of semi-control rectifiers are to convert the single phase 1000 volts incoming voltage to DC and then store it to the DC link here. So here the DC link voltage is about 620 volts. So before storing the DC link voltage, so some of the filtering circuits are present here. The line and sorry, inductors and capacitors, LC filters are present here for filtering purpose, and then that is stored in the DC link here. So the DC link voltage is constant 620 volts. So after that, to maintain the DC link voltage constant, so whenever there is an over voltage, so in order to reduce the over voltages, we are having the brake chopper circuit here. So this is the brake chopper circuit here. Same in the way in the line and traction converter, we have studied the brake chopper circuit. So here also the same. So here the constant voltage would be of 620 volts. So if the voltage increases to 680 volts, then the brake chopper circuit will be in the operation. So when the DC link voltage is 680 volts, the brake chopper will be in the picture. So in this we have a resistor, brake chopper resistor, and brake chopper IGBT. So after that we are having the inverter section here. So it is an IGBT based inverter section. So the DC is taken as an input for the inverter, that is 620 volts DC is taken as an input for the inverter, and the output is given. Three-phase variable voltage and variable frequency output is given. So that is a 415 volts. Three-phase 415 volts is given. So after that, the output of the inverter is filtered using the sine filter inductors and sine filter capacitors, and then given to the auxiliary loads. So this is the block diagram of auxiliary converter. So in the same way, auxiliary converter 2 and auxiliary converter 3. So the working principle will be same for every converter here. So this is about the auxiliary converter block diagram. So these are the parts here: pantographs, vacuum circuit breakers, main transformers, fuse, rectifiers, choke, filter capacitors, and high voltage protection circuits, IGBT based inverter, sine filter. Next, as we discussed, this WAG9, WAG9 heads, WAP7, and WAP5 type of electric locomotives is provided with the three auxiliary converters. So that is of 132 kVA rating each. So each converter is of rating 132 kVA. And physically in one locomotive, two auxiliary converter cubicles are present. In machine room 1, auxiliary converter cubicle 1 is present, and in this machine room 2, auxiliary converter cubicle 2 is present. So which are called as ACU1 and ACU2. So ACU1 consists of one number of 132 kVA converter, so which is called as AC1, that is auxiliary converter, and AC2 consists of two number of 132 kVA converters. So the cubicle consists of AC2 and AC3 and one battery charge. So AC2 and AC3 are auxiliary converter 2 and auxiliary converter 3. And each 132 kVA auxiliary converter consists of, so in the block diagram we have seen this, and this consists of one line rectifier, DC link, and one inverter. And the battery charger is available in the auxiliary cubicle 2, auxiliary converter cubicle 2, and can be driven either by the AC2 or AC3 converters in that cabin. The three-phase output of the auxiliary converters is, as we discussed, it is 415 volts, and the battery charger voltage is 111 volts. So here we can see the sub-assemblies. So here we can see the sub-assemblies here. This is the input section here. We are having input fuse here. So along with the micro switch. So if any damage in the fuse, so it will indicate for the control circuits here. And next after that we are having the MOVs here, metal oxide varioactive. to suppress the input variations, input voltage spike. And after that, here we are having the ELD circuit here. So that is the earth leakage, input side earth leakage detection circuit. So after that, from there, it will be going to the rectifier here. So this is the rectifier module. So that is converting the 1000 volts single phase to 620 volts DC, and that will be stored in the DC link capacitors here. So we are having here three number of DC link capacitors. Here you can see the under the inverter module we are having the DC link capacitors here. Total three number of DC link capacitors. So from that DC link capacitors, the inverter will be taking the input there and giving the three phase output. And for filtering that three phase output, we are having the sine filter inductors and sine filter capacitors. The sine filter inductors will be at the back side of this module, and the sine filter capacitor is here. So after that, the output is taken from here. So we are having the output C2 at the back side and the output ELD here, the earth leakage detection. And after that, from the output we are taking here. So from here we are taking the output for the auxiliary load. So this is the auxiliary converter cubicle 1. So in the same way, auxiliary converter cubicle 2 will be there. So in the same way, so the same components will be there here. So this is the auxiliary converter 2 and this is the auxiliary converter 3. So same, the fuses and micro switches, MOVs, output connectors, output contactors. So in the cubicle 1 we are not having any contactors. Here we are having the output contactors here and battery voltage sensors, auxiliary contactors for operating the main contactors, and CAN cards here, control unit. So here also we are having the auxiliary control computers. So this is the auxiliary control computers here, and this is the battery charger section here. And after that, the rectifier modules, the inverter modules, and the output of this will be taken from this. So these are the DC link capacitors here. So these are the sub assemblies present in the auxiliary converter. So as we discussed, the auxiliary converter components are the line rectifiers, DC link, inverter, battery charger that is present in auxiliary converter 2 and 3, that is cubicle 2, and three-phase output of each auxiliary converter is 450 15 volts, and that of battery charger is 111 volts. So the thyristors are the active switches in the line rectifier, and IGBTs are the IGBTs for inverter and battery charger. So the existing locomotive cooling system has been retained here. So coming to the sub-assemblies and their ratings. So these are the sub-assemblies and their ratings here. The input fuse, so that is of rating 550 amperes and 1300 volts. And MOV, metal oxide varioustor of 2 into 750 volts and 80 kilo ohms. The DC link capacitor 3 into 2.9 millifarads, and OVLR, over voltage limiting resistors, that is of 4 ohms. Sine filter capacitors, that is of 3 into 37.5 microfarads, 850 volts AC, and 3 into 56 amperes. And next, bleeder resistors 5 into 15 kilo ohms, and CTs of rating 1000 amperes by 1 ampere. Sine filter inductor, so 124 micro henries and 185 amperes, and DC-DC transformer, that is of 13 kVA, 550 volts by 220 volts. So this is used in the battery charger. So that will be seen. Next, output contactors 350 amperes, 600 volts, and MCCB of 415 volts, 50 amperes, and 3 pole. So this is used for the battery charger also. Battery charger and input filter inductor. So 200 microhenry, 38 amperes, and output filter inductor that is of 50 microhenry, 114 amperes, and battery charger fuse 700 volts, 200 amperes, and rectifier module thyristor 1190 amperes to 4200 volts, and rectifier module diodes that is of 1410 amperes, 5000 volts, and inverter module IGBT 1200 volts, 1800 amperes, and brake stopper IGBT 1700 volts, 300 amperes. Then saying the input voltage sensors of 2000 volts by 50 milliamperes, snubber capacitors of 0.68 microfarad, 1000 volts, and battery charger, three-phase rectifier diode to 1600 volts to 150 amperes, and HFDC-DC IGBT 1200 volts to 1200 volts and 200 amperes, battery charger output rectifier diode that is of 600 volts, 304 amperes, and DC output fuse is 200 amperes, 700 volts, and output changeover contactors 52 by 1, 52 by 2, and 52 by 3. These are present in the auxiliary converter cubicle 2 as we have seen there. So that is of 1000 volts AC, 265 ampere, and HFDC-DC IGBT snubber capacitor. The snubber capacitor's rating is 0.68 microfarads to 1000 volts, and the battery charger output CT that is of 200 amperes by 100 milli. So those are the ratings of the subassembly. So next coming to the control computer cards. So in control computer cards controls both the line rectifier and auxiliary inverter and performs the auxiliary functions there. And AC2 and AC3 computers can also control the battery charger independently using separate sensors. So auxiliary computer consists of the control and analog signal processing card. So this is the control card here, and DIO, digital input output card, power supply card, and CAN card that is present in only AC2. So coming to the control card, M304B2CC. So this is the control card. So it consists of one 16-bit microcontroller. So running at a higher clock frequency of 80 megahertz or higher than that also. So it communicates with the power modules through CAN communication. The microcontroller communicates the same information of the power module through the CAN communication. So what is this analog processing card is getting the analog inputs are the analog input getting for this control card are the input ELD channel, the ELD channel feedback earth leakage detection feedback, and three-phase earth leak current feedback, and temperature channel, and LOCO battery voltage. So those are the analog inputs going to the control card of the auxiliary converter. So coming to the digital input and output card. So the digital inputs here are the contactor feedbacks here. The contactor 52 by 3 and 52 by 4 feedback, battery charger NCCB feedback, contactor 52 by 1 and 52 by 5 feedback, contactor 52 by 2 feedback, and auxiliary contactor feedback and input to feedback. So these are the digital inputs for the digital input card. So after the digital input card getting the digital input, that will be going to the control card, and the control card process the information and give command to the digital output card. The digital output card is used to drive the contactors. So the enable signals to the contactors are given from the digital output. So we can see here 52 by 1 enable signal to 52 by 52.3 by 1 and 52 by 4 enable signal to 52.3 by 4 and 52 by 2 enable signals to 52.3 by 2 contact. So these are the digital. And next, coming to the power supply module. The power supply module supplies various DC-DC regulated power supplies required for all the modules inside the auxiliary computer. So these regulated power supplies are generated from nominal onboard power supplies of 110 volts DC input. The line rectifier and DC link. So the line rectifier is the interface between the traction transformer and the DC link present in the auxiliary converter. The line rectifier components are such as fuse, surge suppressors that are MOVs, and LC filter and semi-control thyristor rectifier. These are the components of the line rectifier components, and converts the AC input from the transformer to DC and stores in the DC link capacitor bank. The DC link circuit consists of an LC filter that existing inductor in the transformer tank. The inductor is taken from the transformer tank itself, and brake chopper to reduce the overvoltage in the DC link. So AIP in the rectifier module. Analog inputs coming to the rectifier modular. Input voltage feedbacks, input current feedback, rectifier inductor current feedback, and DC link voltage feedback, temperature channels of the rectifier module. And analog inputs in the inverter module are the three-phase output R, Y, and B phase current feedbacks, and three-phase VRY voltage feedback and VYB voltage feedbacks, and the DC link voltage feedbacks and temperature channel in the inverter IGBT. So coming to the inverter section, so inverter acts as an interface between the DC link and the three-phase output given to the auxiliary loads, and the output of the inverter is variable voltage and variable frequencies output with three frequencies of 37, 47, and 50 Hz. And next, inverter components are IGBTs and snubber capacitors, sine filter to reduce the voltage and current harmonics of the inverter output. And coming to the basic control parameters, here are the voltage and fundamental frequency of the output voltage. And sensors provided here are the current sensors on the voltage sensors. And next, coming to the battery charger module. So this is present in the auxiliary converter 2 cubicle and can be controlled with the auxiliary converter 2 and auxiliary converter 3 control system. So here the output of the auxiliary converter, that is the 3-phase 415 volts output, is taken as input to the battery charger module. The 3-phase input is taken, and after that here we are having a 3-phase uncontrolled rectifier with LC filter inside. So here the purpose of the 3-phase uncontrolled rectifier is to convert the input 415 volts to DC here. So the DC of 570 volts is given to the high frequency DC to DC converter. The high frequency DC to DC converter will be having an IGBT here. So that is the battery charger IGBT. We have seen the HFDC DC IGBT. So that DC-DC converter IGBT is used to chop the signal here. So that chops the DC signal here. So after chopping the DC signal, that is given to the HF DC-DC transformer. That is setup transformer that is of 13 kVA. So that the input is of 570, the primary winding, and the secondary, the step down will be of 220 volts. So it will step down to 220 volts here. So after stepping down to 220 volts, here we are having another uncontrolled rectifier unit with LC filter. So these rectifier will again convert this chopped signal to the pure DC, that is of 111 volts and 110 ampere DC. So this is the functioning of the battery charger module. So here we are using this high frequency DC to DC converter and the HFDC DC setup transformer. So this HFDC DC converter, high frequency DC converter, is used to reduce the transformer size, that is the HFDC DC setup transformer size, and this setup transformer is used to step down the signal from 570 volts to a range of 220 volts. So after that it will be again rectified and filtered and given as output of the battery, given as output to the battery for charging. That is given here. So it converts the 14 volt AC from the auxiliary converter into 570 volts DC to this part, and 570 volts DC is converted to triple 1 volts DC in this part here. So battery charger module consists of an individual DSP, that is the digital signal processor for controlling and monitoring purpose. So the DSP will be generating the pulsing signals for the IGBT present in the HFDC DC converter. So the analog inputs that are coming for the battery charger module are the battery charger DC voltage feedback and transformer primary current feedback, DC to DC converter output current feedback, and DC to DC converter output voltage feedback, and the battery current feedback and temperature channel, that is DC-DC IGBT. So the IGBT temperature. So in the battery charger, that consists of three-phase uncontrolled bridge rectifier in the input and high frequency DC to DC converter and uncontrolled rectifier, LC filter, and cable of charging the nickel cadmium battery. So with 30 amps rating and 110 amps limiting current rating. And redundant control from either the auxiliary converter 2 or auxiliary converter 3 computers. And here the sensors provided are voltage sensors and current sensors. So coming to the protections, so we are having the fuse failure in converter, input over voltages or under voltages, input over currents, and ground fault in AC input circuit, over and under voltage protections in the DC link, and DC link over currents, three-phase output overload, and output short circuit three-phase terminals, and ground fault in the three-phase at the load side, and auxiliary converter phase fault, and thermal overloading, and battery charger input MCCB trip. So these are the protections given. Next, coming to the redundancy in the auxiliary converters. So as we discussed, system is a highly redundant system. So we are having redundancy for everything. So from the first and this section we have seen. So we are having the redundancy in the vehicle control units, line and traction converter units. So in the same way, we are also having the redundancy in the auxiliary converter units also. The load distribution among the auxiliary converters. So automatic switching of load from one auxiliary converter to another in case of any failure or in the failure of any auxiliary converter. So battery charger, this can be driven either from the AC2 or AC3 and controlled by either of these computers. So here we are having four operating cases when AC auxiliary converter fails. So the first one is the normal operation. and the second one is when AC1 is isolated, and the third one is AC2 isolated, and fourth one is when AC3 isolated. So these are the four operating cases. So in the next slides, we will be seeing each operating case here. The first one will be the normal operation. So here we can see the auxiliary converters AC1, auxiliary converter 2, and auxiliary converter 3 supplying for different loads. So these are the auxiliary loads present in the locomotive. So the auxiliary loads are mainly the oil cooling blowers, oil cooling blower 1 and oil cooling blower 2 for cooling the oil of the transformer tank and the coolant of the line and traction converter. So these oil cooling blowers are used for cooling coolant and also the oil of the transformer. And next the TM scavenge blower, TM scavenge blower 1 and TM scavenge blower 2. So these scavenge blowers are used to remove the dust particles so coming inside the blower. And next TM blower 1 and TM blower 2, that is the traction motor blower 1 for bogie 1 motor for cooling the bogie 1 motor, and TM blower 2 for cooling bogie 2 motor. And oil pump transformer, oil pump 1 transformer and oil pump 2 transformer. So these pumps are used for circulating the oil in the transformer and to the radiator. And in the same way, water pump converter 1 and water pump converter 2. So in order to circulate the coolant, so we are using the water pump converter 2. So the water pump here, so that is for converter 1 and converter 2. And next compressor, so we are having two compressors in the locomotive, that is compressor 1 and compressor 2, and the other load is the battery charge. So these are the auxiliary loads in the locomotive. So now we will be seeing so which auxiliary in normal condition, which auxiliary converter is supplying for which load. So here we can see the color coding here. The AC1, the auxiliary converter, here we can see that is in the blue color, is supplying for the oil cooling blower 1 and oil cooling blower 2. So the blue and the blue, the color codes. And next, the auxiliary converter 2, which is of a green color here. So here we can see it is supplying for the TM blower 1, TM blower 2, oil pump transformer 1 and 2, and water pump converter 1 and 2. The AC2 is supplying for, auxiliary converter 2 is supplying for these loads. And next, auxiliary converter 3. So the by default, the auxiliary converter 3 load is the battery charger. So that is working, taking the input from the auxiliary converter to the battery charger, and then the compressor 1 and compressor 2, and the TM scavenge blower 1 and TM scavenge blower 2. So these are the loads of the auxiliary converter 3 here. So this is in the normal operation. So next we will see, so when auxiliary converter cubicle is isolated, so which of these loads will be transferred to which auxiliary converter. So when the auxiliary converter 1 is isolated, these loads will be divided between auxiliary converter 2 and auxiliary converter 3. So we will be seeing that. So this is when auxiliary converter 1 is isolated. So when auxiliary converter 1 is isolated, the so in normal operation, the oil cooling blowers are supplied by the auxiliary converter 1. So now the auxiliary converter 2 is supplying for the TM blowers, TM scavenge blowers, and oil cooling blowers. And then the auxiliary converter 3 is supplying for the oil pump transformer, water pump converters, and compressors, battery chargers. So this oil pump transformer and water pump converters, so till in normal operation, these are the loads of the auxiliary converter 2. So now they are shifted for the auxiliary converter 3. So in the same way, when auxiliary converter 2 is isolated, so the auxiliary converter 1 will be taking the loads of oil cooling blower TM scavenge blowers, and TM blowers. And auxiliary converter 3 will be taking the battery charger, oil pump transformers, water pump converters, and compressors. So when AC3 is isolated, so when AC3 is isolated, the AC2 will be taking the battery charger here, and these loads, oil pump transformers, water pump converters, and compressors here. So these are the loads of the auxiliary converter 2 when AC3 is isolated. And AC1 will be taking the oil cooling blower 1 and 2, TM scavenge blowers 1 and TM scavenge blower 2, and TM blower 1 and TM blower 2. So these are the load sharing and redundancy concept in the auxiliary converter. So next, coming to the maintenance in the auxiliary converter. So overall, the unit is maintenance free, and during AOH, that is once in a year, following checks are to be carried out. So blow dust from the entire unit and checking input and output cable connections. Open the unit and ensure the connections of all assemblies. Check for wear and tear of bolts. Check exit air velocity at 4 places in the exit duct, and average velocity should be more than 7 meters per second. So if observed air velocity is less than specified, then the machine room air suction filter should be cleaned as per the standard practice followed by the railway LOCO. So in the same way, auxiliary converter 2 also. So the overall unit is maintenance free. So during AOH, following checks are to be carried out. So blow dust from the entire unit and check input and output cable connections and open the unit and ensure the connections of all assemblies and check for the wear and tear of bolts and check exit air velocity at 4 places in the exit duct, and average velocity should be more than 5 meters per second for auxiliary converter 2 and 6 meters per second for auxiliary converter 3. So if observed air velocity is less than specified, then the machine room air suction filter should be cleaned as per the standard practice of the railway locomotive shed. So next, coming to the protections. So these are the locomotive protection conditions when the vacuum circuit breaker will be opened. The first one, transformer primary return current. So if the transformer primary return current is greater than 800 amperes for 50 milliseconds after initial, so after turn on, so then VCV will be open. So transformer primary current is greater than 330 amperes RMS for 50 milliseconds duration during normal operation, then the VCV will be open. And next, the maximum current relay 78 is on, then VCB will be opened. And when harmonic filter current is greater than 600 amperes, within 1 second after switch on of a harmonic filter, then filter contactor open and VCB will be opened. And next, then when harmonic filter current is greater than 410 amperes, so during normal operation, then filter contactor open and VCB will be opened. And similarly, when auxiliary converter current is greater than 400 amperes, then also the VCB will be open. And next, the converter coolant temperature. So if the converter coolant temperature is greater than 80 degrees Celsius for continuously 10 seconds, then the VCB will be open. So these are the major protections given in the locomotive. So when the DJ will be open due to the fault. So these fault conditions and limits of the faults are given here. So this is about the protections here. So by this we have completed the project MEC 628P2, the control and propulsion systems in the three-phase locomotive. So thank you for giving the opportunity. So if you have any doubts, you can ask.
Hello, thank you, Sarvanand sir.
Yes, sir. Thank you, sir.
So, any questions from your side?
Sir, if auxiliary converter 1 and 2 isolated, then whether all other accessory load can be taken by auxiliary converter 3?
No, sir. So the loco will be in shutdown condition.
Okay, thank you.
So any of the two converters should be on condition.
There are so many protection systems in this loco.
Yes, sir.
Like pressure sensor is there for transformer oil pressure indication or whatever the feedback is taken, it acts as per the feedback, right?
Yes, sir.
Any of the pressure switch or pressure sensor or temperature sensor is failed,
Okay, sir.
then complete traction converter is isolated, right?
Yes, sir. That depends on the temperature sensor. If the temperature sensor in the motor is isolated, so we are having two temperature sensors. So depending on the location, we are having the isolation.
Okay, there are two temperature sensors. One
In
for
the same stator, traction motor stator, we are having the two temperature sensors. So if
okay,
one is in faulty condition, the other will be the redundant.
not about the traction motor temperature sensor. I'm talking about transformer oil temperature.
Okay, sir. So
If
transformer oil temperature is, I think it is only one, sir.
only one, yes, yes. If
Yeah.
that is defective, then complete traction converter or whatever it is, it has been isolated or
So it will be isolated, sir. If the temperature limit is crossed because of the default defective temperature sensor, so then it will be isolated.
I mean both the transformer is for both converters, right?
Yes, sir. Both
So
converted. The
it will
system will
be
be opening the VCB, sir.
system will open the VCB.
VCB direct.
Okay, okay, fine.
In this one, how tap changer will work?
Here we are not having the tap changer technology, sir. In conventional locomotive, we are having the tap changer technology. So this is
Instead
the
of
fixed
that,
one.
okay. Instead of that, what type of technology is it?
So actually, sir, the input voltage, the speed of the traction motors is maintained by maintaining the frequency and voltage levels here, the PWM signals. By switching the IGBT phase, we are increasing the speed of the traction motors.
Sir,
Yes, sir.
how earthing device is working? You are having two capacitance. One is 66K and another is, I think, 20K something.
20K,
How,
sir. Yes, sir.
yes. How earthing device is working?
So actually, we are making a voltage divider rule in between them. Let me show that.
And always current flow.
Yes, sir.
Sir.
So this is the earth leakage detection circuit, sir. So across, we are taking a ratio between this and this. So when a voltage divider circuit is used here, divider rule is used. So here we can see that the formula would be of R1 by R1 plus R2. So if there is any fault on this side, so this resistor will be bypassed. So the ratio will be changed. So that we are giving the limits here. So from that, this ratio is.
Uh, one CT not connected, current measuring device.
CT is connected here, sir.
Okay, sir.
Hello, sir.
Yes, sir.
Sir, how we take the DC link value during maintenance of bar and SR?
During maintenance, how would we check the DC link voltage?
DC link value in on load, na? On load condition में.
Sir, I cannot understand the question. So during the maintenance condition,
Hmm.
how could we check the DC link voltage?
Bar and SR both.
So actually during the maintenance condition, so we are giving a indicator, right, sir? Here we can see the indicator there, DC link voltage indicator. So
Yes.
we have to look at the DC link indicator there. So if the flickering frequency of the DC link indicator is high, so that then you can understand the DC link voltage is present in that. So when the DC link, when the flickering is off, matlab, so if the DC link indicator is in off condition, so that we can see the DC link has no voltage in it. By seeing the DC link indicator, we can.
This is I understand, but how we measure the ये DC link voltage? क्योंकि वो हम लोग का जो शेड्यूल फॉर्म है उसमें वो वैल्यू लिखना पड़ता है.
So that I don't know, sir. I will confirm with the service team.
सर एसआर में तो बस बार के अक्रॉस कर सकते हैं, जो डिश लिंक का बस बार होता है, पॉजिटिव नेगेटिव बस बार.
बार
IGBT
क्या हम लोग
मॉड्यूल्स,
का ये कार्ड के थ्रू नहीं ले सकते हैं क्या?
हाँ IGBT मॉड्यूल्स के, हाँ वो तो देख सकते हैं, डिस्प्ले में भी देख सकते हैं. डिश लिंक का
Display
वोल्टेज
में
डिस्प्ले
देख
होता है डिस्प्ले यूनिट में,
जैसे हम लोग का
LTC एंड ऑक्स का.
जैसे हम
जी
लोग का GTO लोको है उसमें एफ स्लॉट का जो होल है उसमें और ग्राउंड के बीच में हम लोग लेते हैं, लेकिन ये मेधा का
जी,
जो मॉड्यूल है इसमें हम लोग कैसे मेजर करेंगे?
इसमें
ये भी
दो
हमको
टाइप
ऑफ
का आप देख
कंडीशन में
सकते हैं.
लेना है, ऑन
जी
कंडीशन में लेना है, जब लोको
जी
चार्ज में रहेगा उस टाइम हमको लेना है.
जी, एक तो
लिंक
दो
तो
टाइप का
जीरो
हो सकता
दिखाएगा.
है. एक तो आप तो डिस्प्ले के थ्रू ले सकते हैं, डिस्प्ले के थ्रू डाटा शो करता है LTC ऑक्स का डिश लिंक वोल्टेज.
तो बहुत
और
एसआर
अगर
बार दोनों का ही.
हाँ एसआर बार का डिश लिंक वोल्टेज दिखाता है डिस्प्ले में.
अच्छा अच्छा, ओके.
और वो डिस्प्ले के थ्रू देख सकते हैं, ड्राइवर डिस्प्ले के थ्रू. और अगर फिजिकली चेक करना है तो LTC और SR में जो है IGBT मॉड्यूल्स के थ्रू डिसलिंक बस बार दिखता है. डिसलिंक बस बार का पॉजिटिव बस बार, नेगेटिव बस बार,
अच्छा
उनके अंदर आप वोल्ट मीटर लगा के दे सकते हैं,
अच्छा,
जो
वो
भी
जो
वोल्टेज
आपका
चेक
जो
करना है.
ये ऊपर में जो लगा हुआ रहता है वो ब्लिंकिंग करता है. हाँ,
जी जी,
उसी
वो
उसी के
बस इंडिकेशन के लिए, वो बस
इंडिकेशन तो उसी
इंडिकेशन के लिए कि हाँ हाई वोल्टेज में है कि वोल्टेज रिड्यूस हो गया, वो
तो
बस
उसी के
इंडिकेशन के लिए.
उसी के
एग्जैक्ट
उसमें
वैल्यू
हम
नहीं
नहीं दे
दिखाए,
सकते हैं क्या?
एग्जैक्ट वैल्यू नहीं दिखाए, नहीं नहीं सर.
अच्छा, और एक क्वेश्चन था मेरा, कोई बार का जो बोले हो वो जो ब्लिंकिंग करता है, वो अगर
जी
मान लीजिए वो ब्लिंकिंग जो उसका कनेक्शन है वो कहीं से टूट गया, वो ब्लिंकिंग नहीं कर रहा है, तो हमको
जी,
तो नहीं दिखाई देगा जो उसमें कैपेसिटर
तो
में चार्ज
उसके
है.
लिए आप डिस्प्ले से ही एक बार श्योर करके आ जाइए स्टार्टिंग से. ड्राइवर डेस्क से डिस्प्ले यूनिट जो लगा हुआ है उसमें एक बार आप श्योर करके आ जाइए कितना डिस्लिंग वोल्टेज है अभी. उसके बाद ही आप देख लीजिए,
अच्छा अच्छा,
फिर
इलेक्ट्रॉनिक्स ऑन
दिखेगा.
करके ना.
जी जी जी, बैटरी ऑन करके देख सकते
ओके ओके, थैंक
हैं. ओके राइट सर.
हेलो सर, बर
Yes,
वन आइसोलेट हो गया तो कितना किलोमीटर तक गाड़ी चल सकता है?
चला सकते सर, उसका लिमिट नहीं है. दोनों ऑक्सिलरी कन्वर्टर से इतना दूर भी चला जा सकते.
ये पैसेंजर के लिए सर,
ऐसे नहीं.
पैसेंजर लोगों में अगर बर वन आइसोलेट हो जाता है तो कितना किलोमीटर तक गाड़ी चला सकता है, या ब्लॉक सेक्शन क्लियर कर सकते हैं, या क्या?
ऐसा कुछ नहीं है सर. एक ऑक्सिलरी कन्वर्टर अगर फेल हुआ तो दोनों ऑक्सिलरी कन्वर्टर से चला सकते हैं जितना दूर.
अच्छा अच्छा। और सर जो कार्ड के बारे में बता रहे हैं,
यस सर.
क्या कार्ड के बारे में जो बताए हैं आप, वो बर वन का और VCU का, क्या डिस्प्ले यूनिट में कोई फॉल्ट आता है जो कार्ड से संबंधित पता चल जाए डायरेक्ट?
हाँ, पता चलता है सर. कम्युनिकेशन का फेलियर आता है.
अच्छा, कम्युनिकेशन का.
हम्म
अच्छा अच्छा। और सर डाटा लोडिंग जो लेते हैं कहाँ से लेते हैं?
तो उसमें डीएमसी कार्ड, वीसीयू में डीएमसी कार्ड में बताया ना सर, डाटा मैनेजमेंट कंप्यूटर एक कार्ड है.
हाँ
उसमें
हाँ।
आपको दो ऑप्शंस होते हैं. हाँ,
अच्छा
तो पेन ड्राइव कनेक्ट करके डाटा डाउनलोड कर सकते हैं.
अच्छा
या तो और डायरेक्टली लैपटॉप कनेक्ट करके आप डाटा ले सकते
अच्छा अच्छा। ठीक है, थैंक यू सर।
हो।
हेलो सर, एक पूछना था, ये आपका 110 वोल्ट डीसी जो है उससे
यस सर,
कंट्रोल करते वो हाई साइड है या लोड साइड ड्राइव कंट्रोल करते हैं आप?
जो है हाई साइड ड्राइव लोड कंट्रोलिंग।
हाई साइड ड्राइव, ओके।
हम्म,
और सर ये जो ऑक्सिलरी जनरेटर सर्किट में आपने जो डीसी डीसी कन्वर्टर यूज किया सेकंड मतलब
यस सर,
अनकंट्रोल रेक्टिफायर के बाद वो आईजीबीटी बेस है या ऐसा कुछ है वो?
तो वो डायोड से सर, अनकंट्रोल
हाँ,
में सर वो डायोड यूज कर
डायोड
रहे
से
हैं।
है, ओके देखो।
आपने बैटरी चार्जर में पूछ रही थी और ऑक्सिलरी
बैटरी
कन्वर्टर।
चार्ज में,
हाँ, बैटरी चार्जर में तो डायोड से।
ओके।
डीसी डीसी कंट्रोल में आईजीबीटी यूज होता है, डायोड्स यूज होता है इनपुट आउटपुट साइड में, और डीसी
रेक्टिफायर।
डीसी जो हाई फ्रीक्वेंसी डीसी डीसी कन्वर्टर है उसमें तो आईजीबीटी है सर।
ठीक ठीक। और कोई एक लाइन कन्वर्टर अगर फेल होता है तो वो ट्रक कट हो जाता है या वो हम दूसरे लाइन कन्वर्टर से चला सकते हैं?
वो सर ट्रैक्शन मोटर को जो पावर जा रहा है वो रिड्यूस हो जाता है।
ओके।
ट्रिपल VF जो है वेरिएबल वोल्टेज वेरिएबल फ्रीक्वेंसी,
हाँ,
उसमें ट्रैक्शन मोटर को जो पावर है वो रिड्यूस हो जाएगा। बाकी आइसोलेट होगा अगर वो ट्रैक्शन इन्वर्टर और खराब हो गया तो अभी आइसोलेट होगा, नहीं तो नहीं।
अच्छा, ओके ओके।
Okay, thank you very much, sir. Now
ओके
we
सर,
are
थैंक यू।
closing our session, but kindly send the PPTs
यस
to
सर,
Mr. KS Jha's number which he has given to you.
ओके सर,
Thank you once again.
राइट सर, थैंक यू।
थैंक यू सर।